данської неприбуткової організації в Данії проєктує, тестує, розробляє, будує ракети для пілотованого суборбітального польоту. Тобто для того, щоб людина, це ракети, які заплановані на те, щоб нею летіла людина, щоб людина, яка не відмовилась від своєї дитячої мрії про космос, подивилась на нашу планету згори, з космосу, полетівши туди власноруч збудованою ракетою. І це абсолютно феноменально, тому що це ракети з відкритим програмним кодом, open source, ні, не тільки програмний, там ще й інший, є залізний код. І скачавши креслення, кожен з нас колись зможе побудувати цю ракету для себе. Отже, вітайте! Пітер Madsen, Copenhagen suborbitals. Peter, the stage is yours.
Oh, okay. Most of you probably know that we live in a world today, the advanced future, where space is permanently inhibited by man. We have the space station, the International Space Station, with constant people on it, circling the Earth, several hundred kilometers into space. But few people think about the fact that almost half a century ago, we traveled much further away and traveled much faster than we can do today. In the 1960s, people traveled 1,000 times further out into space than they do today. The moon is orbiting the Earth at an altitude of about 350,000 kilometers, so that's roughly 1,000 times higher up than the average satellite in low Earth orbit. And the thing is, it was a very special time because it might have been the product of the Cold War or the fierce competition between the United States and the Soviet Union. The Soviets had launched the Sputnik in 1957 and deeply humiliated the Americans doing so, and they even got the first man, Yuri Gagarin, into space on the Vostok spacecraft in May 1961. So the Americans were deeply dismayed with this and they needed to do better. But when they landed on the moon, they left something up there. The descent stage of the Apollo 11 moonlander carries a gold plate, and it says on it, "Here, men from the planet Earth landed on the moon on July 21st, 1969. And most importantly, it says, we came in peace for all mankind." For all mankind. That means they came in peace for you, me, Ukraine, the Soviet Union, us all, and of course for the United States and all the other about 150 countries on the planet. Up there, not much moves, but in order to go to such a distant place, the Americans had to build an incredible machine. They designed the most powerful machine that has ever been flying, the most heavy object that we've ever launched. It contains more horsepower than any other machine built by humanity. The Saturn V moon rocket burned about 13 tons of propellants during its first day's operation. These 5 engines are the most powerful machines we've ever launched. And here I am. What am I going to do about this? I've got no money. I've got no power. I am not President Kennedy. What can I do? I still think his words about this is very important. Kennedy said, we chose to go to the moon. We chose to go to the moon because not because it's easy, but because it's hard. Because this goal will serve to measure and organize our energies and skills. And so in a period of time, that was only 8 years, they managed to go from literally paperwork to an actual landing on another terrestrial body. And if I look at myself today, I would like to have a challenge like that. I would like to have something to strive for to find the meaning of life. Some distant, almost unthinkable goal that could serve to organize and measure my energies and skills. Not just as an individual, but as part of a team. So I'm looking at my surroundings. This is pictures from a derelict shipyard in Copenhagen. It used to be the BMW shipyard where big ships were built. They built about 1,002 ships until they went bankrupt in 1996. On this spot, I thought we had the right place where we could build, where we could start challenging space and try to do something extreme in the world of amateur rocketry. And I found this hangar. It's 30 meters long, narrow, 10 meters wide. It's roughly the size of the first stage of the Saturn V rocket. And I started a project in there that was aimed at challenging our wildest dreams about what amateurs could do in spaceflight. And to do so, I needed some good friends. I needed some very qualified colleagues. And one of the first to join this project was Christian von Bengtsson. He is educated as a space architect. This is something quite special. He worked for NASA's Center of Manned Spaceflight in Houston, and returned to Denmark when his program, the Constellation program for a return to the moon, was cancelled. And he was here looking for somebody working with manned spaceflight in Denmark, and we have very few actually. We don't really have anybody doing such a program, except this guy, the smiling guy in the picture, who started to talk about building his own space rocket. To do so, you really need a long list of complicated skills. You need people who can do the engines, you need people who can do the spacecraft itself, somebody to produce a spacesuit. That alone is a big project. You need somebody to organize the static testing, the flights. You need to have a launch place. You need to have a lot of things, and you need somebody to sew the parachutes. And you can see them on this picture. We have managed to produce a team that can do that sort of mission. And it has grown beyond this picture, so I need to use this picture because there's not room for all the people that work with it today. So this is a little bit of an outdated picture when we were fewer people. Now, what Christian and I decided to do was our ultimate challenge. What we wanted to do was to build a mission, to produce a mission that would carry a human being into space and safely back. Pretty much like Kennedy said, I believe this nation should commit itself to the goal of landing a man on the moon and returning him safely back to Earth. Our sort of pledge would be that we try to send a human being out of that Earth atmosphere and stay out there, be weightless and enjoy the view, and then return back to Earth. And when I say man, of course, I mean like mankind. It might as well be a female. I'd love to launch a female. We just haven't been able to find volunteers for this homemade rocket ride. Certainly not female volunteers, so I stepped in myself and said, okay, yeah, you can launch me, I'm expendable. So that's a great experience and a great honor to be allowed to do such a thing. What we see in these pictures is the construction of our prototype spacecraft. It was very discount. We built it so that you could only stand up inside of it. There were no room to lie down. And we can see that we are actually welding it. We're actually building it. We're not going to the bank and lending money. We simply started constructing it. And we're presented with a number of incredible, difficult problems, and the only way to deal with incredible, difficult problems that you cannot see a way through is to do something different. When we needed a place to launch our rocket, the problem was that we could not get a permit to launch it at the Baikonur Cosmodrome, because they don't take amateur rockets. We couldn't get to launch it at Kennedy Space Center either. I have to say we didn't ask, but we found out that that probably wouldn't be likely. Or for that matter, any other professional space range. So what we decided to do instead was to go out to sea. So as early in the project as we could, we simply constructed a sea launch ship. We built the ship that you can see in this picture. This is a 12 meters wide, 15 meter long catamaran that can carry a 2-ton rocket far out to sea, outside the rules and regulations of the airspace. And from there, we can launch our rockets, although they're quite experimental and the prediction of the flight can be difficult. We announce our intentions when we're in international water to the Danish authorities, to the Swedish authorities, and even to the United Nations. And this is what you have to do, but that's a very different case than having to ask for permission. Up she goes. This is the most powerful amateur-built rocket I have ever heard of, and it's not even the biggest we're building, but it's the biggest we've flown. This one took off in June 2011, and it went up for an experimental flight that indicated a lot of things. We learned a lot of things, right? One of the most important things of this flight was that it carried with it an inertial guidance system, an inertial navigation system that we have built ourselves, and we are now using this navigation system as the core of our future actively guided rockets so that we can determine where they go. This one gradually veered off course and had a fantastic flight going supersonic on this picture. But we needed to go home and think carefully about how to go on. What was important, apart from the test of the inertial navigation system, was also the fact that we had proven that amateurs can go far beyond the usual amateur range in rocketry, which is like a 2-meter rocket that I can have here, and it goes to 2 kilometers altitude. We are launching with this one a liquid fuel rocket using liquid oxygen as the oxidizer with a lift-off mass of almost 2 tons, and that hasn't been done before. After this incredible experience of launching the Heat 1X, as it was called, we got back home and we started to experiment with a new generation of spacecraft that were engineered so that we could increase the chance of astronaut reusability. Because the first design, where you had to stand up, was suffering from a problem of aerodynamic instability. When it got separated from the booster, it spun very, very fast, it tumbled, and this produces G-forces that are too high for a human to sustain. So we came up with a solution to produce a new capsule with the shape, essentially, of the professional spacecraft, requiring, of course, a larger and more powerful booster, but then we've started to build that too. Nearly every part of the spacecraft is built by ourselves. One of the problems we had was the obtaining of parachutes. We can't purchase parachutes for this purpose because the moment that the parachute producer finds out that it's for a spacecraft, they will require a large budget for developing a custom designed parachute for it. So we actually have to develop our own parachutes. And the Danish law in the field of aerospace is quite complicated, and with regards to parachute testing, it requires, you cannot do an unmanned test. You cannot just put a piece of lead in it and test it over a closed area. You have to jump with it yourself to ensure, quality of production. Suddenly we found a person willing to fly up to 4 kilometers altitude and jump out of the plane to test our parachutes, and we see that it works very well. We conduct a lot of activity involving all kinds of technology for rockets. And in a moment I'm going to show you a video that shows one of the most important activities, which is the static testing of rocket engines. When you develop rocket engines, which is my part of Copenhagen suborbitals, one of the most important activities is to suspend the engine in a test stand and fire it up and measure how it works and see that it doesn't vibrate or things like that. And in Copenhagen suborbitals, we're doing all of these things to ensure that when we actually fly the rockets, we're going to fly correctly and the engines are not going to explode. The 60 tons of concrete in the background of this picture is simply built to prevent the unlikely event that if the engine explodes, then all the shrapnel, all the parts of it will be captured by the 60 tons of concrete walls that are surrounding it. We'll get back to this picture in a moment when we watch the video, but I'll just tell a few more things about what we do in order to ultimately fly human into space. We are developing all kinds of rocket engines. This is one of the engines developed for safety. It looks rather special. It's turned around so it fires up in the air, but it's actually built as an engine to propel the capsule off the booster if anything goes wrong. So we have this engine acting as a kind of catapult seat for the entire capsule. So if anything goes wrong with the flight, if the booster somehow fails, then we fire an engine to pull the capsule away from the booster and save it. The Apollo space program had the same system for the Apollo capsule, but we have had to develop our own engines for it, and this one is a very successful and very powerful engine. It's actually a kind of liquid fuel engine. It's a hybrid engine, and the requirement for it was to be able to power from 0 to full throttle at 200 milliseconds. That's a fifth of a second. And we managed to develop engines that could do that, which are not solid fuel engines. That was quite exciting, and it works beautifully. One of the most demanding, if not as spectacular experiments within Copenhagen suborbitals that we are conducting right now is to to put computers into the rocket to control their trajectory. So we have placed in the nozzle that we see here, I believe this has a laser, yes, you can see it here. We have 4 Strahlruder or jet wings that protrude into the flame, and we use this to steer this miniature rocket. It's only 200 kilos, but that's the next thing that we're going to do, and this one is scheduled for launch in just a few days' time. Right when I come home to Denmark from Kyiv, I'm going out to sea with the whole crew, and we're going to launch this rocket into the air and see if our computerized guidance system can keep it on track. We use the inertial navigation system from the first rocket I showed. We connect this to a computer. It then calculates if there is any trajectory anomaly. If the trajectory gets wrong compared to what we've decided it should go, then it sends a signal to the rudders in the back end. It calculates a signal to them, and then they correct the course. And this is an essential technology in order to fly into space. The rocket that we are ultimately coming up with to send a human into to space is right now under construction at our hangar. Some of the subcomponents we have seen we will get to see in the movie. That's the engine down here. We have made a large work on the development of the engines. We're developing turbine pumps to pump the propellants, and we are currently constructing the tanks that will outdo most of the structure of this vehicle. It's so powerful that it can launch the capsule at the front end with an astronaut inside it to an altitude of about 1,000 of the distance to the moon. But it's still a very good beginning for amateurs to be able to go to the same altitudes as satellites. We don't get into orbit because of the speed not being high enough, but we do get to have a chance of being weightless and seeing the planet Earth as it really should be seen from space. Now this means that we can switch on the video. And before we do that, I just have one more picture. This is how an artist imagines this flight is going to look like. Enjoy that. But at this moment, we're able to switch on the video. And what I want you to notice when you see this video, I think we are missing the sound of the video right now. We're waiting for the sound to be done. They're working on it. The technicians are working hard. What you should notice, am I on still? Okay, what you should notice is that to test such an engine is in fact a teamwork. Lots of volunteers here working for no wages, working many hours a week, go to this island and work hard to have these engines and things built. This is a view through the bunker wall. We are inside a special bunker when we do the testing, and here we can see some of the work being done on the propellants. The engine operates on liquid oxygen at minus 183 degrees centigrade, and it produces a 2,800 degrees hot flame. The technology here is not as advanced as it would be at Baikonur, but the kind of technology is actually developed at about the same time as the large rockets were developed that flies today at Baikonur. This is 1950s, 1960s technology that we're using here, and it really, really works even today. The difference between now and then is that we have access to knowledge, in no small part because of the internet. That means that we can design these things ourselves, and all the subcomponents, as this valve, have become a lot cheaper than they were in the 1960s because of modern production methods. So we couldn't do this in any other time than the time we live in, because you simply need access to hardware and you need access to information, and that's where the internet makes this possible. It has also given us access to all the people who support the program as volunteers. Most of the people on these pictures have gotten to know about the project through the internet. So there's certainly things in our time that makes it possible. Now enjoy the test and enjoy the teamwork. I'm sad about that, but it was very, very noisy. What happened to the sound? Woo! Thank you. Okay, we can shut down the video. There's a few clips of this in slow motion. We're of course not finished with this voyage yet. We keep on working in Copenhagen, and we hope to have many great years of rocket launches, ultimately ending in a manned flight. I'm looking very much forward to it. And one more thing, it's been a pleasure to be here today and enjoy your company, and thank you for listening.
Thank you here, and we do enjoy your being with us. So small present for you. But please do involve volunteers, also Ukrainian volunteers, because we have a lot of rockets enthusiasts. We have a culture of building rockets, and you probably heard about that in Dnipropetrovsk and Kyiv and other cities. So I wish Ukrainian volunteers in Copenhagen suborbitals team, and probably someday Kyiv suborbitals, inspired by Copenhagen suborbitals. Thank you very much. We really enjoyed that. And also the message to everybody in this audience, since this is open source project, we can support it by donating, like every of the open source project Peter is doing, like his submarine or the rockets he's doing. So support it. Keep the great things rolling. Thank you very much again. Thank you.